Welcome to The Explainer. Today, we're doing something really cool. We are decoding the very DNA of our digital world. We're going to explore the fascinating and honestly kind of messy journey of exactly how humans communicate with machines. If you've ever found yourself wondering how the plain text typed out by a programmer magically turns into the seamless apps, websites, and systems that we rely on every single day, well, you are in the exact right place. We're unpacking a massive story of brilliant innovation, severe hardware constraints, and some pretty intense corporate rivalries that literally built the modern software landscape.
So let's dive right into this paradox. Think about it. At their absolute core, processors really only understand binary, right? Just raw ones and zeros. So why on earth did humans go and invent hundreds, honestly, maybe thousands of different programming languages just to talk to them? Why not just pick one and stick with it? Well, as we'll see throughout this explainer, this whole Tower of Babel of coding, it wasn't an accident. It was spawned by a relentless, ongoing drive to solve very distinct problems. Programming languages were born out of strict hardware constraints, the exploding, chaotic dynamics of the early web, and even cutthroat corporate strategies. It is an ecosystem entirely driven by necessity and ambition.
Software development actually spans this massive, sprawling timeline. We're talking way back in the 1840s when Ada Lovelace wrote the very first algorithm for Charles Babbage's mechanical analytical engine. She recognized back then that machines could manipulate symbols, not just numbers. And that timeline stretches all the way to the 2020s and the dawn of AI-assisted vibe coding. It's a breathtaking evolution, for sure. But to really get how software engineering got to where it is right now, we can't just skim the surface. We're going to zoom past this broad view to look closely at a very specific, highly dramatic family dynasty of code that shaped almost everything we use. Section 1. The Great C Family Tree. A dramatic dynasty of code. To really grasp the bedrock of modern computing, we've got to trace this specific lineage of systems languages. It's a story driven by some seriously brilliant minds and, well, some intense rivalries. It all builds up super fast over about 4 decades. Starting in 1962, there was a joint academic project between Cambridge and London universities called CPL. It was complex. Actually, scratch that, it was probably way too complex. So by 1966, Martin Richards created a stripped-down derivative called BCPL just to make compilation a bit easier. That leapfrogged over to Bell Labs in New Jersey, where Ken Thompson created B in 1968, which then evolved into the absolute legend that is the C language in 1972, thanks to Dennis Ritchie. From there, Bjarne Stroustrup expanded it into C++ in 1979, and Microsoft eventually dropped C# in the year 2000. It is a direct, undeniable chain of evolution from quiet university labs to massive global commercial deployments. Now, listen to this quote from Dennis Ritchie describing the B language. He called it, quote, BCPL squeezed into 8 kilobytes of memory and filtered through Thompson's brain. What's absolutely wild here is that these early languages were literally forced into existence by severe hardware constraints. The physical limitations of the computers actively shaped the code itself. The early Unix machines they were working on at Bell Labs, they only had these tiny 4K and 8K memory limits. They simply didn't have the space for a massive, sprawling programming language. The syntax had to be remarkably lean just to survive. But, as hardware inevitably got better and memory sizes expanded, the goals totally shifted. Enter Bjarne Stroustrup in 1979. He wanted to write these really complex systems, but he was incredibly frustrated by having to constantly choose between raw efficiency and elegant code structure. So he took C and he added facilities for object-oriented programming. This essentially allowed developers to group data and actions into self-contained objects, kind of like digital building blocks. He proved that you didn't have to compromise anymore. Code could communicate powerfully with the machine while remaining beautifully structured and, most importantly, maintainable for human developers. So here's the crucial takeaway. Languages aren't always just cooked up for pure computer science or some academic ideal. Sometimes they're literal weapons in corporate warfare. By the late 90s, Sun Microsystems' Java language was absolutely dominating the industry. Microsoft decided to push their own version of Java, which naturally resulted in a massive legal battle. As ZDNet reported back in 2000, when Sun sued Microsoft, Microsoft responded incredibly strategically. They took all their eggs and put them into a brand new basket, C#, pronounced C#. Microsoft developed C# as a direct commercial reaction to legally distance themselves from Java while still offering a very similar familiar experience for application developers. It was a billion-dollar pivot, written entirely in syntax.
Section 2. The Wild West of the Web, from Java applets to ECMAScript.
All right, leaving those heavy systems languages behind for a minute, let's jump to 1995. The internet is absolutely exploding, and those basic, static pages just aren't cutting it anymore. The world suddenly and desperately required a lightweight way to bring interactive, dynamic content to web pages. A scripting language was rapidly developed for this exact purpose, originally called LiveScript. But at that exact same moment, Java was being heralded as the ultimate, future-proof programming language. So, in a pure, unadulterated marketing play, LiveScript was quickly renamed to JavaScript. The really funny thing, JavaScript has very little to do with actual Java. It was literally just a way to ride the coattails of Java's massive hype cycle.
And despite those kind of rushed origins and the intense early browser wars between giants like Mozilla and Microsoft, JavaScript didn't just survive, it totally conquered. It was officially standardized under the very academic-sounding name ECMAScript, and from there, it just spawned a massive ecosystem. We saw specialist libraries like jQuery pop up in 2006 to simplify browser interactions. Then came the revolutionary Node.js in 2009, which broke the mold and allowed JavaScript to run on servers. And of course, powerful front-end frameworks like Bootstrap and React.js followed. This massive expansion is exactly what powers modern full-stack web development today. That means having the ability to use one unified language to build absolutely everything you see on the screen and everything running invisibly in the background on the server.
Section 3. Categorizing the code, climbing the ladder of abstraction.
So, with all these different tools floating around, from C running operating systems to JavaScript powering the web, how do computer scientists actually make sense of it all? Well, they categorize them by generations, which basically just means how far removed they are from the raw hardware. We start right at the bottom, first generation raw binary, the machine's native tongue. Then we climb up to second generation assembler, which translates that binary into very basic text. By the third generation, where we find Java, C#, and C++, we finally hit highly human-readable code. And right now, we are pushing into the fourth and fifth generations, using visual blocks and even natural human language. We're continually climbing this ladder of abstraction, pulling further away from the processor and getting closer and closer to how human beings actually think and communicate.
Section 4. Under the hood. How does it actually run?
Okay, we've talked history, but how does human-readable text actually transform into those dynamic actions you see on your screen? Let's break down the execution process into 3 really simple steps that basically form the beating heart of software engineering. Step 1, you write some code, which is usually just plain text. Step 2, a compiler takes this plain text code and produces something else, essentially acting as a translator. And step 3, that something else is interpreted by a processor or software environment, which actually does the useful stuff, like, running the program. And this right here creates a massive difference in how things actually run. Take your heavy-duty systems languages, like C or C++. You write the text, a compiler rigidly converts it directly into binary assembly code, and your computer's hardware processor reads those instructions. It's direct and it is blindingly fast. But JavaScript? It skips the compiler completely. You just write the text inside an HTML file, and the web browser itself interprets that code on the fly. It's nimble, it's dynamic, and it's absolutely perfect for the web. But what about the middle ground? Well, some of our most ubiquitous, multi-purpose languages out there, think Java and Python, actually combine these steps to get the best of both worlds. When you write Java code, a compiler doesn't turn it directly into machine hardware binary. Instead, it compiles it into something called bytecode. This intermediate bytecode is then read by an interpreter, like the Java virtual machine. This dual-step process offers a brilliant balance. It gives you the speed of a compiled language, but with the immense cross-platform flexibility of an interpreted one. It's literally the reason why billions of Android phones can run Java today. Which brings us to the ultimate question. As we look back at this incredible trajectory, from Ada Lovelace's very first algorithm, through the highly structured C family, right up to modern AI-assisted development tools like Copilot and ChatGPT, a totally new paradigm is emerging. They're calling it vibe coding. You just describe a goal in natural language, and the AI writes the syntax for you. So I want to leave you pondering this. Will the next generation of software even be typed by humans? Or will we just become the architects and creative directors, guiding the machines with our insight and human intuition? The DNA of software is mutating once again, and it's going to be incredibly exciting to see what it builds next. Thank you so much for joining me on this explainer, and keep questioning how the world around you is coded.